Alright, Unit 10, Day 2. We are looking at converting parametric equations with real-world problems here as far as free body diagrams are concerned. Okay, little review. Parametrics are two equations that almost look like a system of equations. One gives the x component, which will tell you how far did something travel x-wise. Okay? And y is going to give you that y component as far as, again, according to this parameter of time that they both have in common, how far y-wise did something travel. Okay, so think of x, y as a location in space, and think t as the time at which it's at that location. Okay, so let's look at the following. Again, anything from this can be on the quiz as well. I feel the quiz is a lot more representative of day 2 more than day 1. Here we go. So when values of t are known, x and y can be formed simply by evaluating for the parametric function. However, to take an x value and find y, it's all going to revolve around solving t first. For instance, if I asked you to tell me when x is 12, then what is y? Okay? So to solve for what is y when x is 12, what you first have to find is you have to find when, that's that time parameter, is x 12. Okay? So it's going to be, oh, thank you, it's going to be negative 12, right? So when is x negative 12? So subtracting 9 over, we get negative 21. And then dividing both sides by this negative 6 is going to give us a positive 21 over 6, which reduces to 7/2, or 3.5. T is 3.5, and the default is seconds. Okay, so 3.5 seconds. At 3.5 seconds, x is negative 12. So now that we know the moment in time, we can solve for what would y be at this moment in time. Okay, so I'm going to go to my y function. It'll be 3 plus 5 times that time that I solved for, which you could put 3.5 or you could put 7/2, either way. And whenever you solve this out, you're going to get that y is equal to 20.5. So the answer for this is y is equal to 20.5. That is what y equals when x is equal to negative 12. Again, remember, you have to find when it happens, and that's going to say that t value in between. Okay, so let's move on. All right, so the next part, we're going to do an equation together, or we're going to do it similar to what we did on number 1, only the difference here is we have x squared terms for time. So we have x squared and we have an x. Okay? So it says the graph given by these functions will cross the x-axis at what point? What in that question tells you how to start? Y is equal to 0. Yes. Y is equal to 0 is this right here, what Gabe is saying as far as that goes. Okay? Alright. So again, crossing the x-axis. It's not going to tell you what to do, but just like Gabe said, that's what we know when y is equal to 0. Okay? So we want to know at what point, that means what is the x and what is the y going to equal when y is equal to 0. So let's first use our y function and solve when the time y is equal to 0. So we have 0 is equal to 8 minus 2 times t. We subtract the 8. We divide by negative 2. And at time is equal to 4, that's when y equals 0. Now that's not my answer. It's like my middle answer, if you will. Because now I'm going to put this parameter of time up here where I see t on both of those equations. And this will tell me what point this is going to be. Okay, I already know that the y value is going to be 0. I just have to come up with what is the x value when t is equal to 4. So you have parentheses squared minus 6 times parentheses will give you your x component or parameter, if you will, your x value. and you're going to plug in 4 here and here so that you get 16 minus 24. And you get what value? Negative 8. So x is negative 8, and this will be your answer as an actual location point. So x, it'll cross, or this graph will cross the x-axis at negative 8, 0. Any questions right now? Again, reminding yourself that you have to find that parameter of time that exists in between them that shares that relationship. Okay? Alright, so now let's look at this one. So for some reason, the times that I've taught this, y equals mx plus b, people struggle to get it to this point. If you can do this, you will be able to check your answers when we do the real world problems on the graph a different way than what I'm showing you today. Okay, I'm showing you today the fundamental level, if you will, but if you're able to really apply this technique, you can do it as far as what you're going to be able to graph, and you'll see what I'm talking about here when we do the real world problems. Let's go and begin. It says, we want to say y equals mx plus b. That's my answer form, okay? What do you not see in this equation that you do in the parametric functions? A t. So we have to find a way to get rid of t and to write y in terms of x. So that you get y all by itself and you have a bunch of x's in constant numbers over here. Okay? What do y'all suggest that we do first? And just by the way, just FYI, participation points are back on. Remember that one thing that you did with Mrs. Hamilton as far as if you got 3 points, I replaced the lowest homework with 100. The highest, I think someone got was 9 points. So they were able to replace 3 homework grades with 100. I will give you that back today so you can see how many you earned in that respect. I've already updated the participation points, and to carry through from the last 9 weeks, I cut them in half to be fair, and whatever was left over, that's how much you're starting with. But today they start as well, okay? Because I want you doing this for the rest of the year, making sure you're good. Okay. Alright, so help me out. What should I do to get rid of t, but ultimately get this as an answer? Well, what do y'all suggest first? Get t by itself. Now here's the big question. Get t by itself from what function? From which one? The x or the y? It's going to be the x. So now we're going to concentrate right here and we're going to get t by itself. Okay, here we go. Subtract the negative. Now, alright, so we're going to solve for t from the x parametric function. So if I divide by negative 3, the one thing that I'll say, that if you do struggle in this unit, which I don't think a lot of you will, you won't, I don't feel like you will. In my opinion, it's because of the algebra 2 skills probably. Okay? Now watch. This separates into 2 different functions, if you will, or 2 different fractions, so that you could have t is equal to negative x over 3 plus 4. Okay? You could write it like this, or you could write x minus 12 over negative 3 like that. Either way, this is where that algebra skills come from. But I'm going to now take this value of t, and I'm going to plug it in where? Into the y function. And I'm going to plug it where I see that t in the y function. Because ultimately, this will replace all t's, get my y by itself, and I'll just have x's left. Watch. Here we go. So we'll say y is equal to negative 4 plus 2 parentheses. And then what we're going to put here was what we solved for t, which is x minus 12 over negative 3. Okay? And now we're going to distribute this 2 so that a positive 2 with x is going to become the following. I have plus 2x minus 24 all over negative 3. All I did was distribute this 2 on both of those pieces, and I have this now. It doesn't go to the bottom because 2 is the same as 2 over 1. So 1 multiplied with a negative 3 will be on the bottom, yes, and you'll get a negative 3 down there. Okay? So if you wanted to split this up, you'd have 2x over a negative 3 minus 24 over a negative 3. This is still adding, and these are those fractions, algebraic pieces that I was talking about. What's negative 24 divided by negative 23 become? What does this become right here? Positive 8, right? Because I'm subtracting this negative 24 over 3. So these two negatives will become a positive, so this is really adding. I have this minus 4, so that at the very end, my equation will become y equals negative 2/3 x, negative 4 plus 8 is plus 4. Any questions from the way that I got that? And the way the notes are, they're a little bit different as far as what was parenthesized or whatever and how it was broken up. There's not just one way to do these fractions. You need to develop that comfortable way of how can I simplify those fractions. But this is your answer for number 3. Questions? Okay, so let's move on to number 4. It says find an equation of the form, and you see this now is quadratic. But we're going to do the same thing. We're going to solve for t so that we have from this x component or x parametric function, t is going to be x minus 3. All I did was get t by itself from x. And now what I'm going to do is I'm going to plug this value of when that happens right here and here for t. So this is what I really have. Y equals 2 parentheses x minus 3 squared plus parentheses x minus 3. Okay, those parentheses are where those t's were at over here in the original equation. Good? Now I have y in terms of what? X, yeah. Okay? Y in terms of x. Now I just have to simplify this. Can someone tell me what x minus 3 squared will simplify? Just that one piece. X minus 3 squared. Because PEMDAS is very important right now. And here are those algebra 2 skills that I'm talking about. What does x minus 3 squared become? What does this become? Because a lot of people say mistakenly, they say x squared plus 9. Okay? Well, it's actually x minus 3, x minus 3 is what you're going to do, but then you have to first, outside, inside, last, FOIL that thing. Okay, what is that FOIL to? Anybody?
X squared minus 9x plus.
Close. X squared minus what? 6x. Yeah, so here we go. So the inside and the outside are both negative 3's, which this will become a negative 6, and then the last terms is a positive 9. Don't let algebra 2 escape you, especially in this unit, because you'll use a lot of algebra 2 in that respect, okay? So I have x squared minus 6x plus 9, which is still going to be multiplied with 2. And we're still going to, let's distribute this where we get plus x minus 3. I just got rid of the parentheses on that. Then we'll distribute the 2 and combine like terms and we're done. So we get 2x squared minus 12x plus 18 plus x minus 3. And if you combine like terms all together, you get a negative 11 plus 15. And this would be your answer for that one. Simplification, algebra 2. That's all we're doing right now. Okay? Any questions? All right. So let's move on to these 3 problems, and then we can get to real-world application as far as parametrics are concerned. All right. It says for each description, write the parametric functions for the linear graph. This is very important right here. Let me ask you this. Are all parametric functions, are all of them linear, yes or no? They're not. They start off as linear, like when you start learning them, they're mostly linear, but they can be quadratic, cubic, and all that other stuff. All right, let's do number 5. I need to come up with an equation, parametric functions, an x and a y equals. Okay? Can someone tell me what I should write with for x equals? Let me help you out. At time 0, the x is 8 and the y is 2. Close. You're close on one of them. Let me show one more time. At time 1, x is 3, y is 4. You with me? Now, what Michaeli was saying, mx plus b, what did this letter tell us when we were using it back in Algebra 1? What did it tell us? What was it used for? An intercept, a y-intercept, and it told us where to start. It was your initial value. Where do you start? Now, what I want you to do is envision that there's two kind of mx plus b's going on here, but I want you to think of it like b plus mx. Don't write anything yet, okay, on both of these. Don't write anything yet on your notes. So you tell me, where does x start? 8. And you always need to go to when time is 0. That's where you start. So x will start at 8. You with me? Where does y start? 2. Now, this letter right here tells us how does it change each jump. You with me? So m, look at these numbers. How did the x value change? If I'm analyzing x, how did the x value change on each jump? Minus 5. So x-wise, m is a negative 5. Okay? Only we're dealing with parametrics now, where the parameter is not x, it's time. How does the y's change? Plus 2, right? So you're going to have plus 2t. Done. Fairly easy if you can methodically just go through it, okay? Now that we have this in table form, if you notice, it made it a lot easier when I made the table. And I suggest that you do that if you struggle with it being given to you like this. Okay? All right. How do we start this off? X equals what? 12. Y equals what? Negative 4. Now we're going to show how does x jump each time. So each time, how much is x jumping? Negative 8, right? Be careful with the negatives because the negatives are big mistakes here, okay? Because it'll carry through and make the whole thing incorrect. Y, how does it change? Plus 7. There's your two parametric functions. Yeah?
Same for the last one. How it's plus 2.
So this is changing. So y-wise, it's jumping up by 2. So from there to there was 2. It would be 6, then 8, then 10. You know what I mean?
Oh, okay.
And then over here, it's jumping up by 7. So jumped up to get 3, jumped up by 7 to get 10, and so on and so forth. Okay. Other questions? Okay, so let's do the graph now. Because we got to be able to identify all 3 different ways, okay? Where do we start x-wise with the graph? At the top left, right? And what is the x value there? Negative 2. Okay. Y-wise, where is that at? 3. Now, look at x. How are you changing? Not each jump like this, but each second. How much x did you change? Well, you went from -2 all the way to 1. So you changed what? Positive 3, right? Positive 3. Because you went to the right 3. So it'll be a positive 3t. Do we get it? And then y-wise, how are we changing? -2. See, guys, these are the fundamentals, and I got to make sure I go through them step by step because everything else stems from this. And if you can get these pretty sound, the real world problems are a lot easier. Otherwise, it's like, it's a nightmare, okay? But you'll be fine. You'll be fine. All right, here we go. Real world application. Okay? So pretend that you're this golfer and you're about to hit this ball at this certain angle between the ground and where it's going to fly. And however much this shows, that's the strength at what you're hitting this ball with. Already you should be thinking vectors. But here's the thing. How could we know how much of this will get traveled? Well, there's your x component, if you will. It's going to be, just like you did with vectors, the magnitude times the cosine. The only difference, extra added piece, is now you're going to have a time interval. You with me? And then finally, y-wise, this is confusing a little bit, at least when I first saw it. Y-wise, as far as how high, so this says how far. That's this right here. This says how high. How high is this ball at any given point in time? That's the application. Okay? Here we go. The way this is drawn right now, and if you look at this, will it ever hit the ground with these two that I have right here? Yes or no? Will it ever hit the ground? No. This is as if you were in space. And if you hit it and there was no gravity whatsoever, it would travel this vector right here infinitely to the end of all time, to the end game. All right, with that being said, gravity now gets played into it to where we know that the height is not going to just keep getting higher and higher and higher. This ball will get higher and higher and higher, and then at a vertex of a quadratic that has a negative in front of it, which means it's a reflection across the x, it means that this particle, this projectile, will reach an apex and it will come back down. Hence, that's where this negative 16t squared comes from. Okay? Now, right here, you see the same thing, only you tell me, what does this h represent? This is as difficult as it gets, by the way, is this h. If you can set up everything, it's easy. Okay? And I think it's really easy. And I'm going to show you how to use a calculator, not just programs, but how to do menu solve features and stuff like that. Can someone tell me the h? The height of what? The starting point. So this is going to be the starting height. Most of these problems that you do will start at a height of 0. So you won't see anything there. You won't have to put +0. But a good majority of what we do in this unit now will not start at a height of 0. Okay, let's do our first example problem. Soccer player. Some kids dared Wanda to try to kick a soccer ball over the fence into the neighbor's yard. Here we go. Using colors is huge in this unit. If you are one of those people that likes to use different colored markers, because it'll keep track of everything. So 20 feet is as far away as that fence is. And that fence is 6 feet high. So let's go ahead and say that this is 6 feet. And drawing the diagram is the biggest thing. If you could draw the diagram, I mean, the rest is pretty easy. So Wanda uses a key with an initial velocity of 40 feet per second. So here we go. she's going to kick it at an angle of 30 degrees. So when she kicks it, she's aiming like this vector, if you will. Okay? And the vector's strength, which we used to write as the magnitude in vectors, is going to be 40 feet per second. Okay, and last but not least, the angle is 30 degrees. See, you're not going to have anything. You're going to have to draw the drawings, okay? We're creating those angles, creating that position, and all that other stuff. The only difference now in this unit, guys, is that this ball is going to do this. And we want to figure out, is it going to clear by actually going over? Or could it maybe miss the mark? Or could it hit the fence and bounce back? We're going to figure all that out. And this is where the calculator comes into play, okay? First of all, let's write the equations of the path, otherwise location, of the ball. What is the x parametric function? Anybody? What do I write for the x parametric function? I'm trying to write this for this real world problem. What do I write? 40 times the cosine 30. And then what? T, right? Very important, that T. Okay, let's put that right there. And guys, you don't have to put these dots here. I just want you to know that that means multiplication. In the calculator you do, but when you write it, you don't. So what will the y component be? 40 times the sine, because it's y, of 30, and then what? T minus 16t squared. Now listen, should I add something to this? Why not? Because I'm starting at ground level. So if you start at the ground, it's the same as plus 0, but we don't need that. Okay? Alright, so now that we have our two parametric functions, what window setting, and this is where we're going to switch over to the calculator. You don't have to sign in, but you do have to follow very closely as far as what we're doing, because like I said again, you haven't used the calculator, I don't think you've used the calculator to this level as far as with like Algebra 2 stuff that you've done in the past. Alright, so let me go ahead and sign in real quick. 8 period 5 5 1 2 3 4 5. Alright, so now you'll see my calculator. And here we go. Follow me very closely, please. And if you have questions, ask them immediately. I don't want to go back and repeat myself. Here we go. First of all, what we're going to do is we're going to graph a parametric function. So, home to, menu C, okay, always clear that calculator. Okay. Next, press 1 for new document and 1 for a calculator page. Now I'm going to add a graphing page by pressing Control, Doc, which is add a page, and then press 2 for a graphing. Now that I have this right here that you see is not, this is not parametric. This right here that you see is actually rectangular. It means this is x and this is y, or f of x. What we want is a parametric function. And watch. We're going to press menu. We're going to press, I believe it is analyze graph. No, not analyze graph, my bad. 3, graph entry. The graph entry is going to be parametric, so we're going to go to 4. And notice how they change to parametric functions. Okay? So now I have an x and a y location depending upon the parameter that we've been talking about of time. Very important. I want you as a default to change this to 0.01, which we'll do in just a bit. But right now what I want you to do is enter those functions that we just got. 40 times the cosine of 30 degrees. Now, let's slow down. Yes, I do. So right here, this needs to change to degree. Even though you change the calculator to degree, it won't change the graph to degree. I'll repeat that. Even though you could change this one to degree, like home 5.2, if I were to change this to degree, and I were to show you, going back to my document, that's now degree. You see this as degree now. If I go control right, my calculator's graphing page is not on degree. So I have to independently change that by pressing menu, 9, and this second one right here needs to change to degree. And then make it your default. Okay? Again, make it your default and then press OK. Now, if you notice at the top right hand corner, it is now in degrees and you're ready to rock and roll. Okay? Let's go. 40 times the cosine of 30 degrees. You don't have to put the degree symbol, but I'm going to multiply by t. Please, 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 don't make the mistake of putting what letter there? X. Don't make that mistake. A lot of people do, okay? Our parameter is time. And then I'll go to y, and I'll put 40 times the sine of 30 times t minus 16 times t squared. Now don't press enter yet. We're going to change our default of our step. We're going to always change this to 0.01. And then t is time. How long do you think that ball is going to be in the air? At most. Not 20 seconds, that'd be a big. 5 seconds. Let's do 5 seconds. So we're going to put 5 right here and press enter. Now, this is learning the calculator. This doesn't show the complete trajectory of that soccer ball. I want the whole thing. Let me press tab and go up. It's this one right here. I'm going to put 5 right there. Okay? We're about to. So, and I want you, press escape to get rid of that thing. I want you to understand what options you have. Watch. Menu, 4 for window, and you could put 8 for trig, because these are trigonometric functions, if you will, and it shows this, but I don't like the way that looks. My option is probably the best one is menu for A, for fit. I want to fit that as much on that graph as I can. Now, my goal is to see this kind of right there. I'm trying to show just quadrant 1. So from here I can develop like a window that I would want it to show. Okay? Now, let's change this to a customized window setting. Here we go. I want you to go to menu, 4, 1, and what do you think the x-min will always be? No. The x-min is always going to be 0 per se, because we're going to start at when x is 0 per se. You with me? So we're going to say 0, and then what's the x max? How far do you think that thing can go? 50. Let's do 50. Y min, what do you think for the most part? Most on average, our y value is going to be when we start? 0. Because this is starting from ground level. And then, how high do you think that could probably go? Let's do 30. And see, there's the graph right there as far as the entire thing is concerned. Now, if you don't like the way that looks, you can change it up a bit and say menu 4, 1. I don't think it would go 30 feet high. Let's do something like, let's say 10 feet high. And it's showing it a little bit better. This shows you the kick's trajectory and its path in the air. Any questions right now? Okay. So now what we're going to do is over here on our notes, go ahead and put the window settings, and some of you already have this copied down, but the window settings that we came up with were 0 to 50 as far as x is concerned, and 0 to 10 as far as y is concerned. Our t-step is 0.01, and then our t-min is 0, and our t-max is 5. That's 0 to 5 seconds. The lower this number is, just FYI, the cleaner your graph is going to be. If that number's too big, it's not going to look like a parabola. It's going to look like a bunch of different lines, like jagged lines instead of a nice smooth curve. So you want that to be as low as you can. Now, the trace feature. Here we go. This is the last thing that you'll learn with the calculator. Ready? As far as for this application. So, to me, I think this is the fundamental way that you can use a calculator, and I like the way that this shows it, but you have to understand how to use it. Here we go. We're going to press menu, 5, 3. And we don't want the trace step to be automatic. We want to insert a value, and we're going to enter the value of 0.01. Menu 5, 3. And then we'll press OK. Now it means when we go and we scroll this, and we scroll through this graph, it's going to go 0.01 each time. There we go. Menu 5, 1. Now you can start moving this left or right, and it will show you where it's at, how high it's at, how far it's at. Let me go ahead and show you. This right here is the x value. Okay? This shows how far away this is at that moment in time. This is how high is this ball at that moment in time. Go with me? And this tells me how many seconds did it take to get there. How many seconds was it in the air until it got to this location right here? How's that? Okay? And it says, how far does the ball travel? Can someone tell me, how would I see how far the ball travels? What is it that I'm concerned with? What is 0? When it crosses the x-axis. We want to know, when it crosses right here, which of these numbers, you tell me, will be 0? Why? Okay, so keep going to the right. And when you get that y value to say 0, stop. There it is. So at 43.3 feet away is how far it traveled, because that's when it hit the ground. That's huge, okay? So we're going to put when y is equal to 0. So when y equals 0, x is equal to 43.3 feet.
Oh, I never got to 0.
The t-step might have not been on 0.01. So make sure that the t-step is on 0.01. And the t-step being on 0.01, guys, is in 2 locations. Right here on my input, I can change this to 0.01. Or more importantly, when we press menu 5.3, changing that to 0.01. You with me? The smaller you do it, the more precise your numbers can get. Okay. Then it says, how long does it take for the ball to hit the ground? So when we did this, menu 5.1, whoops, I went too far. You tell me, how long did it take? It took 1.25 seconds. Remember, that's your parameter of time. So you're going to say, when y equals 0, t was equal to 1.25 seconds. And then how high was the ball when it was 20 feet away, and did the ball clear the fence? So guys, this right here, when it's 20 feet away, what is that? X. So when x equal 20 feet, we want to know, what is y? How high is it? You with me? So you can do this the way we did these over here in our notes earlier on, you can find one more. At a specific x or whatever y value, you could see as far as what the y would be if we found the time, or we can just simply go to the graph and see what is it going to be when x is 20. Okay, so let's go to the graph. We'll scroll back. We'll find when x is 20. You don't. I would keep the trace to like 0.01. You know what I mean? But whenever you get to 20, went a little bit too more. It doesn't go right on 20. I see what you're saying. So to get right on 20, let's get a little bit more exact. So let's go menu, 5, 3, and instead of 0.01, what could we do? 0.001. And then press OK. So now when I'm going to the left, there it is. You can see there's 20, there's another one. You see what I'm saying? There's 3 of them. It's going to be an approximation as far as this goes. You with me? It's going to be an approximation, and it gets you about 6.22 feet. So you see 3 different ones. 6.22 feet is how high above the ground it is. When it's traveled, right here, this 20. So the ball is right here in line with the fence once it's traveled 20 feet. The question is, how high is it? You know what I mean? Is it right? Is the ball here? Or is the ball hitting the fence? Is the ball, would it be underground as far as insinuating that it was a low, small kick? Like, where's the ball Y-wise? Well, we get 6.22. Does it clear? Yes or no? Yes, it clears it by 0.22 feet. So you say yes, clears by 0.22 feet. Yes?
Would we ever factor in the size of the ball?
No. In physics 2 in college, yeah. And frictional coefficients too, as far as air resistance, the rotational, centrifugal forces and accelerations and like that, you don't do that on the basic level of parameters. For you to get to that level, you got to understand parameters first. Okay? But yeah, there's a lot more forces dealing with that play into it. Any questions on this? Now look, when I asked you 20 feet away, what we could have done for this equation is we could have solved for t and then plugged it into the other one and got the y exactly. Okay? Let me show you that one time on the calculator so that you can see how you could do it. So 20 cosine of t would look something like this. So we have 40 cosine of 30. So 40 times the cosine, I said 30, right? 30. Let's say times t. Okay, this is my parametric function for x. And when I want it to be 20 feet away, look, menu, 3, 1. When it's 20 feet away, we are going to solve for t. So comma t. This will happen at 0.577 seconds. Guys, we saw that over here on the graph that it happened that way at 0.577 seconds, right here. Okay? It's just more exact the way I did it on the calculator page than on the graphing calculator page. Okay? So now that I know when it's doing that, I can go to the other equation and I can plug this value in for t. Does that make sense? Okay? So I could do what 40 times the sine of 30 degrees times 0.577 minus 16 times 0.577 squared. And you see that you have 6.21, so this is more exact. Y'all see what I'm saying? And as far as the way I did that 0.577, what I could have done is just copy and paste. So I can go up there. Let me Control C. It's just that T that I have there. I needed to take it out. And then Control V. Do you see how I'm doing this, guys? And then just taking out that T's, because otherwise it's going to jack it up. And then you can come over here and put Control V, just like you do on your keyboard. Control C to copy, Control V to paste. And then you get that more exact answer. That's the exact answer. Whoops. I hope some of you want to do this. Otherwise, the graph is good enough. But this is exact. The graph is more exact, approximate, if you will. Questions? All right, so the biggest problem that we have for today, and then we'll finish up with the circles stuff, which is fairly easy, really easy, is this one right here, okay? This one is kind of putting everything together. All right, here we go. So, Mike hits a baseball with a velocity of 180 feet per second at an angle of 15 degrees. The outside fence is 400 feet away, and it's 10 feet high there. Okay? The upper deck of the seating begins at 420 feet from the home plate, and that is 30 feet high. And last but not least, Mike hits the ball 3 feet off the ground. There's a lot going on there. And if you don't know vectors, it's hard to even get started. Okay? So let's write the equations to model this first. Okay? So what would the equations be for the x parameter? What would x be? 180 times what?
Cosine.
15. Yep. So 180 times the cosine of 15 degrees times t. Okay? Let's do the y. What would that be? 180 times the sine of 15 degrees times t minus 16t squared. Plus 3. Nice. Put that in your notes if you need to. This is your starting height. Say again? 16t squared. That's that inverted parabola, right? And 16 is that gravity, because if you derive it, it's 32 feet per second, which is gravity. 9.8 meters per second. Same thing. Okay? And then negative because it's falling. We good? Okay. Now, with this, so I believe it's this one, go a little crazy on 6th period, and I drew it a little bit crazily. A little. Oh, did I go too far? Okay, there it is. Okay, so let me show you what's going on. Same problem, only I drew it all out. And let me highlight these. As far as I'm hitting the ball with a velocity of 180. So you see this 180 right here. I'm going to try to color coordinate best I can. That's the strength that I'm hitting this vector at. The angle that I hit it was 15 degrees. And you see this right here is 15 from the horizontal. It started off 3 feet above the ground, which is right here. You see that it's 3 feet above the ground. And now what I want to do is I want to see all the way to the outfield is 400 feet. That's this line right here. Okay? And it's 10 feet high. So this 10 feet high is right here. Okay? And then furthermore, the 420, if I kept going on, that little bit more is here. At that point in time, it's 30 feet high. Can you understand the graph now? Okay? So now what we're trying to do is, this is 10 feet. How far does the ball travel? One, how far does it travel if it were to go all the way until it hit the ground per se? You with me? So what is it that we're going to do? We're going to set what equal to 0? Y. We're going to set, to see how far it traveled, we're going to set y is equal to 0, and guess what we're going to solve for? We're going to solve for t, to see when would the y value equal 0. And when we get that value, we're going to plug that t into our x parameter so that we could see how far did it travel. Okay? So, for the sake of instructional purposes, I'm going to do the graph again. And I'm going to do it with this with this new equation that was given. Here we go. Control right. Let's press delete 3 times and press yes. So I'm teaching in the calculator. We'll press tab, and it'll be 180 times the cosine of what? 15, right? Times t. Now it'll be 180 times the sine of 15 times t minus 16 times t squared plus 3, because it started not at ground level. Let's put this to 0, 1. And let's put this, let's keep it at 5. The way we did the other one. Okay. My graph is nowhere to be seen. How can I show the most of my graph right now? By doing the fit. Menu, 4A. This will fit as much of the graph on there. And what I'm trying to focus on now is quadrant 1.
Press tab again.
Yeah. I wanted to focus on quadrant 1. You see how it changes the t-step? I don't like the way it does that, but we'll change the t-step when we're doing the trace anyway. So let's try to change the window up some on the, so we can show just quadrant 1. So let's go menu, 4, 1. And what do you think I should change? Definitely x min should be what? 0. Y min should be 0. And x max, what do you say? 600. And y max, what do you say? I mean, because it showed it on the thing right there, right? 50. Let's try 50. Perfect. So there's the trajectory of the ball. And if I want to see how far does it travel, you're going to press menu 5, 3. And let's change this back to 0, 1. And then we'll say menu 5, 1. And we want to go all the way to see how far it traveled. We want to go all the way where y is going to equal what? 0. There we go. Yeah.
I don't see anything on my calculator.
I'll show you here in just a bit. Did you put x or did you put t?
I put T.
Okay, hold on just a bit. Let me go to 0. So this right here is at 0.23. This is at negative 0.23 or 0.256. So we want to change menu 5, 3. We're going to do it just like we did that other one to 0, 1. Make it a little bit more exact. So now I can go to 0, which is very, very close to that right there. So it went about 517 feet. Okay, until it hit height of 0. That's pretty much close to 0. How long did it take for it to get there? It would take 2.98 seconds. So the ball was in the air almost 3 seconds. Okay, if it went that far. Okay, the other questions on this. Okay, so it will travel 517 feet because on the graph, that's when the y was 0, whenever it was at 517 feet. So this is y-wise and this is x-wise, how much did it travel? Okay. Now the other part said, how or does it go, oh my gosh, does it go over the fence? So we need to find out when x has been traveled 400 feet, okay, so when x has been traveled 400 feet, that means it would reach this big old huge wall, if you will. Where's the ball? And like I did that other time, as far as if that's the ball, and I were to move this around, if I were to move this around, is the ball here, 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 here? Where is it at in relation to the trajectory? Okay, so you're going to go over here on the graph, and you're going to make your x component, if you will, you're going to make it what? 400. Okay, so menu 5.3, I'm going to change this step, otherwise I'll be here forever doing this. And we're going to go all the way to 400. Let me ask you a question real quick. How many of you already solved it the other way? Okay, if not, we'll try it here in just a bit. I want this 400. Oops, a little bit too far.
Can you just make a line where they're supposed to intersect so you can find the exact number?
Align how?
Like, put in, like, x is equal to whatever.
You can't. That's the big question here. She's saying, I understand what you're trying to do. The reason why you can't is this is not x equals. I know it shows an x value here, but it's more so. Yeah, it's not rectangular. This is parametric. So you can't see it that way unless you develop the graph, the function to be this. Remember how in the very beginning of today's notes we made this into that y equals mx plus b? If we do that, then we can do this location. But we won't know the time. We would have to go back to solve for whatever that time is. Yeah. Either one. So now at 400, you see that it's going to be 25 and a half feet high. This is how high, this is how far. You tell me, does it clear it? Yeah, it clears it by what, 5 feet? Or 15 feet. So it clears it by 15 feet. And if we wanted to know, does it clear the second or the upper deck, you just go all the way to 420, which is around there, and does it clear it, yes or no? No, it's around 22. It's nowhere near that. It's nowhere near that. What was it? 30 feet high that it needed to be? Yeah, it needed to be 30 feet high, and it's only here about 22 feet. You with me? Okay. Any questions? So let's do it on the solve feature. If I wanted to see, does it clear, and this is what I hope you do. This is what I hope you use it. I'm going to do this menu solve feature with this equation right here, and I'm going to set x equal to what number for the first part? 400. So we're going to set this equal to 400, and it'll be the solve feature of when does that happen. Okay, so let's go to the calculator real quick. So we're going to say menu 3.1 solve when an x of this has been traveled if it's 180 times the cosine of 15 degrees times t. And we're solving for t. It takes 2.3 seconds to travel 400 feet horizontally. Now if I want to know how high is that, I can just plug it into the equation that's dealing with sine. You with me? So you could say something like this. Let's say, I'll just do it. 180 times the cosine. Actually, you know what? This brings up a point right now. Do you see how I keep having to delete that t? So those of you who want to save a little bit of time, do insolve menu 3.6. And now you don't have to delete that t. You can use this in your second one by doing 180 times the sine of 15 times this answer, right? Because this is my time, right? And then it'll be minus what? 16t squared. And then plus 3. Guys, did it clear it? It did, because the fence was how high at that point? It was just 10 feet high. We're talking about the 400, not the 420. Okay? So at the 400 on the graph, which is, let me do that right here. This right here, when it traveled 400 horizontally, it had a y value of 25.5, which I needed what? 10 feet. So it more than cleared it easily. And if I want to do the menu solve feature for the now 420 feet away, you can do it like this. So let's go up here, but instead of it being 400, we're going to say when it's 420, how long did it take to get there x-wise? And then I'm going to plug that into my sine function, which is 180 times the sine of 15 degrees times that t value minus what? 16 t squared plus 3. And it's 22 feet. So when it reached this distance of 420, the ball was 22 feet high. Okay, so this is when it reaches it. And it's 22 feet high when we needed it to be 30 feet that you see over here. Oh, you don't see anymore because I highlighted too much. But anyway, it doesn't clear for the second one. My hopes, again, the other classes aren't learning what I just showed you. This menu solve feature, they don't use in the other classes. The menu solve feature, it allows you to find it exactly, and I think faster, than clicking and clicking through a graph. Okay? Questions? All right, so we'll end with our last part of today, which is, and then I'll give you your quizzes or tests back. Guys, don't forget, please, homework, bug and spiders, that projectiles, that make sure that that is ready and done. It is a lot of work. Don't procrastinate on it. It is a lot of work, but you can watch this video to make sure that you're good to go. And you know that Eagle Time is weird this week because of star testing, so make sure you're doing homework at home. And you'll have a quiz the next time I see you. All right. Equations of a circle. Look at the following. We know that a locus of points, basically infinite number of points, that are equidistant from a given point. So all of these are equidistant from that given point. Those are the radii, if you will, of that circle. The center that you see here from the graph was negative 6, 2. I got it from the graph. The radius, the way I can see what a radius is I draw the circle. Believe it or not, those of you who... Okay, I'm going to put an orange point. Is that on the circle, yes or no? It's not. A lot of people think that the circle is everything in here. But that's not what a circle is. A circle, how about now? Is the point on the circle? No. This is on the circle. All of these points are on the circle. You with me? So with that being said, if I looked at it almost like north, south, east, west, I can see that any one of these will be the radius. I can easily see from a graph. Okay, that's the best way to see it as far as speed is concerned. Now, notice the form. Oh my gosh, who did this? Notice the form as far as how we're going to... What did they write? Did they write 6th period as the best class? I think they did. All right. The form that we're used to is right here, algebra 2. Our center was negative 6, 2. And notice how you have opposite in parentheses. You had a positive 2 there. You have a negative 2 here. And the equation is equal to r squared. Because this, whoops, is what you remembered and learned from algebra 2. What we're going to do now is we're going to convert this. It's easy to go to general form. Because all you're going to do is make this squared by having 2 of them. Make this squared by having 2 of them. FOIL each piece. Add all combined like terms. And last but not least, set it equal to 0. And put it in x squared, y squared, xy number form. But what we learned today is this part right here. The center, which used to be here and here, is now here and here. In the radius, notice that these two numbers are the same. The two numbers that are here and here, if those are the same, it's also a circle. Okay? You see that the radius is 4 for the x, and you see that the radius is 4 for the y. Any questions on what we did today? Outstanding job, guys. That's it.